Let's look at the mean, variance, and standard deviation of a discrete random variable. A discrete random variable takes on only finitely many values, or infinitely many values, which can be counted. For example, these random variables are discrete: the roll of a die, number of children, number of cars owned, number of pets, age in years. Notice that these tend to be things that you can count. Roll a six-sided die and let x be the outcome. Find the mean of x. Here are the possible outcomes when you roll a six-sided die. This is the probability of each outcome, assuming the die is fair. So here's how we find the mean of x. It's the outcome 1 times the probability that you get a 1, namely a sixth, the probability of a 2 times the probability that you get a 2, which is also a sixth, plus 3 times a sixth, plus 4 times a sixth, etc. And it works out to be 3.5. So the average roll of a die is 3.5, 3.5. The mean of a random variable x is sometimes called the expected value of x and is denoted by this symbol. That's the expected value of x. More generally, for a discrete random variable x, the expected value of x is going to be the sum of x f of x, where f of x is the probability of that particular value of x. In other words, x is what we call the probability density function, or PDF of x, or the density function, or the probability distribution. Roll a six-sided die, for example, and let x be the outcome. Suppose I pay you x squared. How much should I charge you if I want to break even in the long run? Well, let's find the expected value of x squared. The expected value of x squared is going to be the sum of x squared f of x. So in this case, it's 1 squared times the probability that you get a 1, plus 2 squared times the probability that you get a 2, 1/6, plus 3 squared times the probability that you get a 3, 1/6, etc. Add all of those up and you get 91/6, which is 15.1666666. In other words, it's $15.17. That's how much I should charge you if I want to break even in the long run. Let's roll a six-sided die and let x be the outcome. Find the variance of x. The variance is a measure of how much variation there is in a variable. We saw that earlier when we looked at the variance of a set of data. It's a measure of how much variation there is in the data. Now, we learned a formula there. Don't use that formula here. We have a different formula. In this case, when we want to find the variance of a random variable, we use this formula. It's the expected value of x minus mu squared. And this formula makes sense because if all the x's are clustered around the mean, then there's not going to be much variation. So we'd expect the variance to be small. And indeed, the variance will be small, because if all the x's are clustered around the mean, then x minus mu is going to be small, so x minus mu squared is going to be small, and we'll end up with a small variance. Now here, the mean is 3.5, so what we calculate is the expected value of x minus 3.5 squared. There's another formula for variance which I prefer. Mathematically, it's going to be equivalent to this formula here, but I just find it easier to use. The variance of x is the expected value of x squared minus the expected value of x squared. And again, it's going to give you the same answer as this formula. So in this particular case, the expected value of x squared, we know what that is. That's 91/6. We saw that a moment ago. The expected value of x is 7/2, 3.5. So we have 91/6 minus 7/2 squared. In other words, that's 91/6 minus 49/4. Find the least common denominator. We get this, and that works out to be 35/12. So that would be the variance of the variable x. Okay, let's roll a six-sided die. A 1, 2, or 3 earns you $1, a 4 or 5 earns you $2, and a 6 earns you $20. How much should I charge you if I want to break even in the long run? So again, these are your possible rolls. These are the probabilities of those rolls. A 1, 2, or 3 earns you $1, which means the probability that you'll earn $1 is 3/6. A 4 or 5 earns you $2. So the probability that you're going to earn $2 is a 6 plus a 6, namely 2/6. And the probability that the payout is going to be $20 is 1/6, because that's the probability that you get a 6. So again, let x equal the payout. The expected value of x is this. It's the sum of x, f of x. And what's the probability that you earn $1, $2, $20? That's 3/6, 2/6, 1/6. Okay, so let's calculate this. So the summation of x, f of x, is going to be, again, x is the payout. X is not the roll. X is the payout, because we want to find the mean of the payout, not the mean of the roll. So x is the payout. So this is one payout, $1. The probability of that payout is 3/6. Another payout is $2. The probability of that is 2/6. And the other payout is $20. The probability of that is 1/6. Add all of that together, and we end up with 27/6, which is 9/2, which is 4.5. Okay, so that would be the expected payout. If I charge $5, for example, I'll make 50 cents each time we play, on average. Let's find the variance of the payout, x. Okay, well, we saw earlier that the expected value of x is 9/2. Let's find the expected value of x squared. The expected value of x squared is the sum of x squared f of x. So it's going to be 1 squared times 3/6, 2 squared times 2/6, plus 20 squared times 1/6. Okay, add all of that together, we end up with 411 over 6, in other words, 137 over 2. The variance of x is the expected value of x squared, which is 137 over 2, minus the expected value of x squared, which we saw a moment ago. That's going to be 9/2 squared. So when we multiply that out and find the least common denominator, we get 274 over 4 minus 81 over 4. In other words, 193 over 4. So that would be the variance of x. Why is this variance so much greater than the variance of the roll of a six-sided die? Okay, this variance is 193 over 4. It's just a hair under 50. Whereas this variance, the variance of the roll of a six-sided die, that was just a little over 2. Variance is a measure of variation in outcomes. The roll of a six-sided die gave us outcomes between 1 and 6. The dice roll game gave us outcomes of 1, 2, and 20. Granted, the chance of getting a 20 was only 1/6, but even so, this leads to a much larger variance, roughly 50, as opposed to the earlier variance, the variance of the roll of a six-sided die, which was just a little over 2. Okay, let's find the standard deviation of the payout. The standard deviation is also a measure of variation. It's just the square root of the variance. So since the variance is 193 over 4, the standard deviation is the square root of 193 over 4, which is root 193 over 2. The symbol for standard deviation is the Greek letter sigma, okay, written here. Because variance is the standard deviation squared, the symbol for variance is sigma squared. So not very creative there. By the way, in the US, the average slot machine payout, return to players, what we call it, varies from casino to casino and from state to state. It's generally between 89 and 94%. In other words, for every dollar that's put into a slot machine, roughly between 89 cents and 94 cents is paid out to the players. Not a really great deal, if you ask me.